If you're a weather enthusiast, and since you're listening to AMS on the air, I think there's a very good chance that you are, then do we have some exciting news. A global community of weather enthusiasts is waiting for you. The AMS Weather Band, a new initiative by the American Meteorological Society, is a vibrant online community of radar watchers, double rainbow hunters, teachers, learners, and everyone in between. Gain cutting-edge insights about the weather that interests you the most. Share your love of science from wild weather stories to jaw-dropping photos and videos. Gain exclusive access to weather experts, plus lots of fun content and interactive features. Learn all about it and join today at weatherband.org.
Welcome to AMS on the Air. I'm Jeff Rosenfeld.
I am Irene Sands.
And I'm Dakota Smith. We're ready to podcast about all things weather, water, and climate.
The other thing, and usually what I'm more involved in, is looking at low-level winds and tornadoes. We gather a lot of data, but it's a really hard data set to get to because you're trying to get really close and you're also trying to get instrumentation in the path of the tornado. Tornadoes sort of have that same appeal. There's a lot of things that people don't know about tornadoes and I've been working really hard to learn about, but it's just challenging to do. So it's interesting to get in sort of that challenging observational arena.
Hey there, and welcome back to AMS on the Air, the official podcast of the American Meteorological Society. On this episode, we are featuring another great interview from the 2020 annual meeting in Boston. Jeff had a wonderful conversation with Dr. Karen Kosiba, a professor at the University of Illinois Urbana, Champaign. In this role, Dr. Kosiba manages a fleet of doppler on wheels that travel the world monitoring a variety of severe and impactful weather events. Just a note, at the time of the interview, Dr. Kosiba was stationed at the Center for Severe Weather Research. If you have even the slightest interest in severe weather, you are in for a treat. Enjoy.
I'm here today with Karen Kosiba of the Center for Severe Weather Research, and this is kind of exciting for us because Karen is the ultimate in severe storm junkies, right? Would that be a fair assessment, or should I say you're a research scientist instead?
The ultimate research scientist in severe storm junkies? No, getting the research scientist in there is nice.
Is there any difference between a severe weather researcher and a severe storm junkie? What's the difference, if there is one?
That's a good question. I mean, certainly people who are researching severe weather obviously love it and love being out in the field. I think just the big difference is I'm out there also trying to collect data. So there's specific problems that I'm out there trying to answer when I'm in the field looking at tornadoes.
So what's the data you're looking for these days?
Oh my gosh, I feel like the same data we've always been looking for. No.
It's changed a little bit, I think.
It's changed a little bit, but it depends what part of the tornado problem that you're looking at. So, I mean, there's the tornado genesis problem, which people are still actively out there trying to understand how tornadoes form. And we know that some steps in the tornado genesis process, but there's still a lot out there with regards to thermodynamics and different fronts in the supercell system that people still don't really understand how that contributes to the process. The other thing, and usually what I'm more involved in, is looking at low-level winds and tornadoes. So we gather a lot of data, but it's a really hard data set to get to because you're trying to get really close and you're also trying to get instrumentation in the path of the tornado. And since people are doing that, you have to give a little bit of leeway so they can deploy stuff and get out of the way. But what we're trying to do with that is we're trying to link with the winds that we see near the surface or at building level and how that relates to what we actually measure with radars, which is usually above building level.
So how high is low?
How high is
or
low?
how low is low? Maybe I should say that.
How low is low? So we have instrumented pods, which we call them, which are a meter in height, which I'm going to say is probably a little too low, but it gives you an idea, though, of what the winds are getting like too near the surface so they can bound your other observations. And then with radars, we're trying to measure winds probably 10 or 15 meters above ground level. So we're trying to get really close so we can scan through at 10 or 15 meters above ground level.
Now, I don't even know if I've seen much imagery at 10 to 15 meters. So that sounds like that's
you never
not
come to my talks.
Yeah. Like today's talk, for instance, here at the AMS annual meeting.
Yes, exactly.
But 10 to 15 is really low for a radar, right? So, but with your Doppler on wheels, is that sort of the routine height you're looking at, or you can?
No, that's not the routine height that we're looking at. That's what we're trying to get. And it's hard because you have to get close. So you have to get within a kilometer or two of the tornado. And only certain tornadoes really lend themselves to getting that close. You you have to feel obviously safe doing that. And normally what we're looking at more so is, 30 or 40 meters above ground level. But we are still really trying to get that building height radar data set. So we have a few, but we don't have, a nice statistical sample of that.
So for 30 or 40 meter height, how close do you have to be? How close is
I would
close?
say 5 kilometers away or something. I mean, which is sort of standard what most mobile radars are. So if you see other groups out there, they're usually staying back about 5 or so kilometers, which is, good for getting low-level information. But again, we're just really trying to link what's actually happening below that level, because the few data sets that we have gotten below that level actually suggest that some of the stronger winds are occurring closer to the surface than we previously had thought.
Yeah, this is what intrigued me about your abstract from from today's presentation.
Right.
That the max winds were lower than I was thinking.
Yes.
So what was the previous idea, and what are you now thinking in terms of where the max winds are?
Yeah, so the previous ideas mostly have been based on numerical modeling, so large eddy simulations, and people sort of have been scaling what they see in their models to what that should scale to in the atmosphere, because large eddy simulations they've gotten a lot better in terms of integrating models, but it's not like, you're looking at a full physics, storm model and stuff like that. So it's a little bit of scaling that you have to think of in your model. And they're thinking, below 100 meters, but probably closer to 100 meters, for the strongest winds. Whereas what we're seeing in the few observations we've gotten, that we've actually seen winds, that are strongest at 5 or 10 meters above ground level, which is sort of remarkable. Some of it, and I should say, caveating, that some of it probably depends on your tornado structure, which is why it's great to get many, many more samples, because all tornadoes don't actually look the same, have the same structure. So they certainly might have different wind distributions near the surface.
Now, I was debating this at the bar last night with Chris. So I don't understand what you mean by tornado structure. Because when I think of, in the old days, you would look at photos of tornadoes and they say, well, that's what's visible because that's where the dust and dirt sucked up or whatever. But really, it's still the same thing. It's just what's visible. And so it sounds to me, and sure, there were like wedges and there were ropes. And
Right.
But that was more a life cycle type thing in my mind. But it sounds like there's more to it than that when you talk about structure. Like it's spinning winds, right? I mean, what's to say about structure?
Ultimately, yes. I mean, it is, spinning winds. But there's differences in, and this is actually came a lot from laboratory, again, in numerical modeling. And then all these groups, my group, Howie's group, have been taking mobile radars out, and, suddenly you're seeing, oh, it's not just, an in and out, a circle, type structure, what you're thinking of in a tornado. You're seeing some wind maximums over here, some wind maximums over here, and they're all maybe rotating around a bigger wind maximum. Some of these tornadoes have an updraft throughout their entire vortex. Some have an updraft, and then they turn to a downdraft at some point.
Really?
Yeah.
Up at higher altitudes?
Yeah. Some have a downdraft basically all the way to the surface in the center, and what we call a two-celled vortex. So there's different manifestations of vortices, and they don't necessarily imply having the same winds.
Okay, but if there's a downdraft in the center, like a hurricane, sort of.
Not like a hurricane.
Not like a hurricane.
Yeah, not
So
like a hurricane. Not
picturing?
driven that way.
No.
So this is a dynamical driven downdraft in the center. So yeah, so I'm like using my hands and nobody can see this except for everybody that's here.
It's helping us.
So you can have these, the in and up is sort of what people conventionally think of. But dynamically, what could start happening is you start to get a breakdown in that flow, and a downdraft starts getting further and further downward. Again, you still have in and up on the sides of these multi-vortex tornadoes, but it's that central downdraft that you could start getting a reversal of flow.
Is that because of such low pressure?
It's because you can't really
bottom, or-
sustain the flow.
sustain the flow.
So you're actually getting an instability in the flow where it starts to break down, and you get then that building of a downdraft.
And how are those structural differences manifested in the strengths of the winds that you're seeing?
So a lot of that right now is still numerical modeling, theory type stuff. So in theory, your strongest tornado actually would have updraft and at some point a central downdraft. And that because of the swirling winds and, like I said, it's sort of laboratory modeling of what would be most dynamically strongest. But again, laboratory and numerical modeling, they don't totally translate to nature. So a lot of these structures that we're seeing in nature, it's not like there's necessarily a one-to-one correlation with what you're seeing in models or what you're seeing in the laboratory. things like that you're missing in a laboratory simulation or in a modeling simulation at the tornado scale is you're missing downdrafts and you're missing, changes in time that are impacting these things. So there's sort of different suggestions about how that may impact stuff. The thermodynamics, all this stuff just doesn't come into play a lot of times when you're doing some of these idealized modeling. That doesn't mean, again, we're getting a lot of information from numerical models. It's just figuring out then how that translates to what we're seeing in the atmosphere. And then in the reverse too. So for people who are doing theory, both of these can't exist alone. Both people need each other to understand what's happening.
When you were younger, I understand you were sort of interested in severe weather, right? Was it lightning, tornadoes? What was the thing that got you interested, do you think?
Interested / frightened.
Yeah,
and I think a lot of people come to that. Yeah.
Yeah.
And I feel like that's sort of a common, I thought it was scary, and then I learned more, and it's still a little scary, but it's really intriguing. So I grew up in the Chicago area, and I know you could say there's probably a lot of famous tornadoes that happen there, but not really except for one, the Plainfield one, during my time. And I didn't even know it was happening, I remember. And suddenly all these people showed up at my grade school, and I'm like, what happened? And they're like, oh yeah, their school got demolished by a tornado. I'm like, oh, really?
Wow.
So close? I didn't know that.
Yeah.
But yeah, I was sort of more fascinated with lightning because that was something you saw more. And now I would have known, of course, that there was a tornado there, but there's no media like it is today. People aren't tweeting about all this kind of stuff, so you have no idea. And lightning, obviously, was a lot more accessible because you could just look out the window and it's, a really cool lightning storm. And actually, at some point when I was looking at figuring out what to do, when I finally decided I wanted to go to meteorology, there's obviously a lot of problems in lightning too, and how that gets generated. That's interesting. And don't ask me to talk about it. I'm just saying. And then tornadoes sort of had that same appeal. There was a lot of things that people don't know about tornadoes, and that I've been working really hard to learn about, but it's just challenging to do. So it's interesting to get in sort of that challenging observational.
So you think
arena.
It was inevitable you were going to be drawn to something that was a big challenge? Like that was really where you were headed no matter what it was?
I think it's a combination. So again, it's sort of cool that, you're working on something that you find challenging and that people have been working on and they find challenging. And again, things are progressing, but it's in some ways, you're not getting those big, huge, moments pushing things forward, but you're getting a lot of these incremental stuff. So you have to be a little patient, building up this stuff. But the other thing I like too, and I think I would have always been drawn to, is I like working with a bunch of, I'll say different things. So I like, working with the radars, and I like, doing the analyses, and I like just kind of having a variety of stuff, but also being able to get out in the field and collect data.
So when you're out in the field, you're collecting data, but you're not looking out the window.
I'm definitely not.
That in and of itself is kind of a transformation in the way you deal with weather. Obviously everybody goes through that sort of transformation as you learn more and you're more aware of all the issues involved. It's a much more complex thing than just looking out the window. Being a scientist is more than that.
Yeah. No, it's definitely much more complex. And then, I feel responsible for people that are out there with me. So keeping track of what they're doing and making sure we're getting the data we need also, as part of that transition too.
So when you look ahead and you're managing all these issues, and you got to be thinking, how can you make the next breakthrough or whatever? Or you're thinking, you think in terms of how can we just keep incrementally move forward incrementally. See what I'm saying? It's like it's a mentality that you kind of set in that is more realistic, but also sustainable.
I think so. Maybe other people, are looking for the big breakthrough, and that'd be great if that happens too. I'm not, but when I, sort of look at stuff, all these new toys come, people have UAVs now and can sample places that we couldn't sample before, and these drifter sound balloons, which is a different type of sampling that we haven't been doing. So you never know what technology and sort of people's innovation is going to take you to. So I still think it's going to be incremental, but I think it's incremental in the sense we're better targeting what things that we should be looking at. And either as we're modeling or as tools become available, we're sort of, we've gotten the broad picture from a lot of the stuff previously, but now we're sort of really focusing in on very particular questions or very particular aspects.
Now, also, I wanted to talk about toys a little bit too. So, because when I ever think of your center, I think of toys,
yes,
and you have the coolest toys, and have for many years. So, I'm wondering, cows, sows, barns, all this kind of stuff. What are the new toys that you're looking forward to? You mentioned UAV. You slipped that in there. I don't know if that's part of your
right. So we haven't been doing UAVs. We've been working. with radars. And yeah, if you haven't gone to Josh, my colleague's talk this afternoon, he'll talk about other things we're thinking about. So, the cow, yes, we've decided to go with the barn theme because it just worked out. Yeah, so the difference is, the Dows are X-band mobile radars, and they fit nicely on a truck, and you can get really great resolution with them, and they're very nimble, and we do a lot with them. So, they're great for that. They can sustain a lot of wind. But the one big thing is that in very heavy precipitation, so in some of these supercell thunderstorms and hurricanes, what happens at X-band is you attenuate. So that means you can't see the back end of stuff. So you can't see the back end of the supercell, but if you're looking at the tornado, that's sort of okay. But you can't see the back end of stuff. In hurricanes, you really can't see far. So you're really looking at, what's in the sort of nearest 10 kilometers from you, and you're not getting anything past that. So with a C-band, which is the cow, C-band on wheels, the idea here is preserving a lot of what the Dows do. So there's good dual pole data, we could scan fast, but we also still want the good resolution that we get with the Dow. So we also want this 1 degree beam. And in order to do that, you have to have a bigger dish. So what's been devised is we have a dish that we assemble on site. So it's not nimble in the same way with the Dows. So you can't do the same type of, tornado chasing with that. But for a lot of other things, it's pretty good. It takes us a couple hours to set it up. And then we're operating with a 1 degree C-band. And it's the only portable 1 degree C-band there is.
I hope it's a perforated dish so that it doesn't blow over. And I'm just wondering, how do you hold that thing down?
Yeah, so yes, it is a big sail, but we have outriggers, so we have a very nice big base with our big sail.
Otherwise, you're tipping cows.
Yeah, we're not tipping cows. I don't want to be in a tipping cow. So that's been great, and you also get better clear air. There's a lot of better things you could do with a longer wavelength radar. So then the idea, of course, is that if you could do it with C-band, even longer wavelength is S-band, which is even more penetrating. So those are your 88D radars, your S-pole radar at NCAR, but your 88Ds are obviously stationary, and your S-pole radar at NCAR takes several weeks to set up. So now we're thinking about, doing a trailer. So bigger, because we're getting bigger wavelengths, we need bigger dishes. But doing the same type of thing that we've done with the cow is that basically we're going to have a bigger dish, assemble it on site. Again, it's a couple hour setup, so we're not in a chasing mode, but that's fine, again, for 90% of the projects you're doing. Mm-hmm. And then you're also getting good resolution, and you need a couple of them, only because you can't make a dish that big with an S-band and keep it on a truck. Yeah. So it goes to a 1.5 degree beam as opposed to a 1 degree beam. But if you have a couple of them and you're close to what you're looking at, your resolution starts becoming comparable to a 1 degree beam.
Now, you keep talking about getting close, and I'm wondering, isn't it hard to hire people to work with you, or does that make it easier?
No, people love, except for hurricanes. I always am like, we don't get that many repeat customers in hurricanes. Everybody always goes out once, and then they're like, this is sort of miserable. But even myself, the first time I did a hurricane, I'm like, oh, this sucks.
Why?
Oh, it's
a
terrible.
Hurricane. Why? Because it's humid?
Yeah, it's humid, it's windy, you're stuck in the truck for 24 hours.
Oh, my.
You've made a decision, hopefully, that it will not flood, because we're parking very forward in our hurricane stuff. Because what we're looking at is we want the winds as it transitions from the ocean to the shore. So we're getting as close as we possibly can without, going under.
You don't have pontoons?
No pontoons. We do bring life rafts.
So you got a hurricane, you got a tornado genesis issue and a hurricane exodus issue.
Yeah, exactly. A hurricane, yeah. So, hurricanes are kind of miserable, and you have to go to the bathroom sometimes, and it's just windy and wet.
We won't get into that.
Yeah, no, I'm saying like all in general, because you're sort of trapped in a truck for 24 hours, and then after 24 hours, whatever's receding with the water and stuff like that.
Wow. Well, it sounds like you've got a lot on your hands just staying safe, but also getting the data, and it's really cool what you guys are getting. So
thanks.
I appreciate the update, and we're going to keep looking for the latest toys.
Most definitely.
Okay.
We will have
Bring them to the exhibit hall too.
Yes.
Great. All right. Thanks a lot.
Okay.
And that wraps up another episode of AMS on the Air. Thank you so much, Dr. Karen Kosiba, for telling us all about her fancy severe weather gadgets. If you want more information about this episode, you can find it online at ametsoc.org. And to get this podcast in your app feed, click that subscribe button. And if you want, follow us on Facebook, Twitter, and Instagram. We're at AMS on the Air. All right, thanks everyone, and happy weather.